So, good evening, class. So, we will continue again, maybe for about 35 minutes, Hannah. 35 minutes. So, we will rest for a while. I think we will, okay. 35 minutes. 20, 25 minutes is better. 25 minutes. Okay. Okay, so, we need to, when we want to start the design, sorry, can you see my screen or not?
No, sir.
Okay, dengar kan?
Dengar.
Okay, nampak tak sekarang?
Nampak, sir.
Okay, thank you very much. So, when we want to start to design, I mean the motto, we need to know what is the geometry. So, from the chapter 2 code, when we talk about magnetic circuit, um, I usually to mention we need to deal with the spatial or geometry. So in order to get the dimension, we need to use the estimation method, whereby we call analytical calculation for the motor dimension. And then analytical means we analyze it, so that's why we call analytical. Actually, it's just a mathematical calculation. Then we will start from the non-overlapping winding machine, because if let's say we directly go to overlapping winding machine, it will be a little bit confusing. It's better we go for easy first. So assume that we have a 12 slot 10 pole PM Brussels machine, and yeah, we always start from double layer. We won't start at a single layer. From single layer, change to double layer will be very not so easy, but from double layer to single layer, it will be easier. So we always start from double layer, and then this is the item that we need to assume first. Of course, for your mini project, this item, I mean this material, will not given you directly everything. Some of it you need to calculate. For example, we need to determine these two things. Then the rest will be given. This will be given, given, and given. So magnet remanence. Magnet remanence is the capability of the magnet when it is not excited, which means it's at a rested position. For example, we have a neodymium ferrum boron. Okay, we have a neodymium ferrum boron. Once we excite it with a coil, okay, initially Br is 0 because no excitation. After that, when we excite it, okay, it will become Br equals to 1.12 Tesla, even though we take off the excitation. I equals to 0, even though it becomes a simple magnet. When we see the simple magnet, it's the north and south pole. And then it will, when we put steel near to it, it will attract it, right? And then the capability of creating the flux is the 1.12 Tesla. This is the power, the power of the magnet. And then relative permittivity means the characteristic of the magnet. And then air gap thickness is the motor anesthetic. Itu panggil apa? Let me see any now I have yeah, yeah. Let's take this one. I got here. Okay, so where are we? Okay, the air gap thickness. Okay, air gap thickness is this one. This is the air gap thickness. And this is the air gap thickness. And then some more. The magnet thickness. Magnet thickness. Let's say this is the magnet, right? Okay. Let's say this is the magnet. So this is the iron. Steel. Okay, this is their thickness. This one also have a thickness. Okay, the thickness of it. And then anything else? Saturation. Okay, saturation flux density iron. If let's say you still remember in EP208 or the magnetic circuit, when the steel at the saturation level, there will be a lot of losses. So which means when we design the motor, we want to make sure all the fluxes flowing through this area, okay, are just ngam, just optimally uh, at the saturation limit. Yeah, my mouse. All the fluxes flow through the iron side. They will give the saturation limit of 1.6 Tesla. It won't too low. Too low means maybe if let's say the optimum the motor that we design, they give the VR, V mode here. We call V mode, is about maybe 1.2 Tesla. Then it will become under design lah, because it is not reached to 1.6 Tesla. If let's say at the optimum, the motor that we design, the V mode, V mode means the modulus magnetic flux density lah. It gives about 2 Tesla, which is more than the 1.6 Tesla. So it is over design. And then stator bore radius RSI. Okay, RSI is here. So RSI, RSI is here. This is RSI. Okay, R means radius. Is measured from the center. It's measured from the center. Anything else? Theta outer radius. Okay, outer radius. This is the RSO. RSO, which means the length the length from here to here. RSO. And then axial length means the length of the motor, which is kepanjangan dia, the length of the motor. For example, okay, let's say the motor is this side. Okay, so the length here. This is the axial length. Kepanjangan motor, the length of the motor. And then number of slots, yeah, for sure, and the number of pole lah. The number of slots, for example, we have how many slots? Slot 1, slot 2, 3, 4, 5, 6. So this is a 6 slot lah. How many poles? 1 pole, 2 poles. So this is a 6 slot 2 pole machine. Okay. And then determine, first of all, we need to know whether this type of a motor is a non-overlapping or overlapping winding machine. Usually we start from the number of slots of pole, and SPP, this is the NS divided by NT. So by using 1, 12 divided by 10 is 1.2. As long as it is less than or equal to 1.5, we will choose the correspond of 1. When correspond of 1 means we will only wind the winding from here, go back, and come up here. It won't go to here and then go to the other side. Come on, like this. No. Right? So as long as it is less than or equal to 1.5, we need to choose the correspond as 1. Then when the correspond is 1, we call non-overlapping winding machine. Because it's only coil like this. We only coil. We only coil like this, right? We coil like this. It's not overlapping. It is not coiling with the other two slots. So then we need to calculate the average flux density in the middle of the air gap. Why we want to calculate in the middle of the air gap? Because when we want to get the energy, okay, when we want to get the energy or rotation, what we need to do is we excite the current for the winding. Then the field will react with this. So when the reaction is the stronger the field can cause to this middle of the air gap, the better the performance. That's why we don't want to calculate other magnetic average value, but we only calculate the middle of the air gap, because we want to know how good the flux can flow through the flow from the tip, and then go to the air, and then go to the rotor. Also, that's why we focus on the middle of the air gap. So first of all, we will calculate the average flux density in the middle of the air gap, Vg, whereby it is a Vr divided by 1 plus mu R LGHN. exam or test will come out. Equation will not given, yeah. So by using equation number 2, we just substitute lah. So what is the BR? What is the mu R? What is the HM? LG. What is the HM? Then we calculate the average value. Also, it's a 0.8298 Tesla. Remember, this one is 1 milli. It's not 1 meter. I already voiced out here. Please don't ask in the WhatsApp group. Because every year I already mentioned this one. Then a lot of people keep asking. That is the problem. Which means you are not listening. When you are not listening, I cannot blame anybody. Okay, and I also don't want to say that I don't want to make you difficult while you cannot answer, cannot calculate it. So this is 1 milli. This is not 1 meter. Okay. So okay, before we go in deep on finding all the variables, we need to understand. I mean, go through what is this? Okay, this one I actually draw myself during my study in PhD. So first of all, we need to know how the flux goes through. How the flux. So the flux is actually this the bold color one. It is flowing like this from the rotor pole. Let's say this one is the north pole. North pole. Rotor pole. It go out and then it will flow to here. Flow to here. Then go in. Then go in. Then split into two. Okay, then go, then come back again, like this. Come back to a south pole, okay, and then go to the here. This is a south pole. Then this one is a south pole. Then come here. South pole is go in one, right? North pole is go out one. This is how the flux flow. Why we say so? Because the flux. Oh yeah, I forgot to introduce you. In this analytical modeling, we only use phi equals to VA. Okay, and then remember that the B, it must be 90 degrees to the area. Let's say this is the area. It must be 90 degrees. That is 90 degrees. We only use this one, and then we only from here we need to know how to find the area. The area can be square. Okay, let's say square is x by x, then it will be x times x. If let's say the area is a rectangular, x times y, so between x times y lah. If let's say the area is a circle, so it is only pi r square the area, or pi d square divided by 4. How to get it? Pi d divided by 2, then square it. And mouse. Pi d divided by 2 square. Then we get a pi d square divided by 4. So, and then we need to know how to find the circle, the jari, or the perimeter. So, as the length from this point go to this point for a circle with a radius of r. So, we only use 2 pi r. Then, if let's say we want to find an arc, S equals to radius times theta, which is S equals to r theta. Then this theta must be in radian. This is the basic. Okay. Then slot pitch is an angle for one theta feet. Angle for one theta feet or one slot lah. One theta slot. Okay. And then this is how the fluxes flow and this is only on this plane, Okay, only on this plane. So inside the same, it will go like this, and then go through here, go through here. For example, at the back, you go inside, and like this, you go in, split again. it happens along this length of the motor. Then this part is called stator. Now we only focus on stator. And then, so this one is a flux for stator pole, stator pole. And then this is flux for the X, which means just a random number. And then and then this is flux for stator pole, same. Then flux for stator Y, stator yoke. Because this part is called stator yoke. This part is called stator yoke. And then we have RSI, stator inner radius, stator outer radius. SI is in stator inner radius. This one is the stator outer radius. And then we have a WTP, width of the tooth tip. Tooth tip means this is called tooth tip. This is called tooth tip. And then we have a width of the tooth end. And then we have a width of the tooth body. Tooth body. Then we have a stator yoke. Stator yoke. Now this is all the terminology. LA is the axial length. Axial length. And then A is area. This one is called stator teeth. Area of stator teeth. Area of the tooth body. Area of the stator yoke. Okay. So area is something like, for example, area of the stator, area of the tooth body. We need to find this one times this one. This one will be the area. For example, area of stator yoke, we need to find this value times this value. So it's area. This one also the same. The arc here times the length here. Now become the area. Also the same here. The length here times this, the length here, will get the AX. So this is how we need to know what is the picture first before we go into the solution. So first of all, we will find the tooth body width and WTB, and then remember that the first thing we need to use is actually by using flux equals to VA. Which means this is the source of flux, plus 10 Tesla. So when it comes to here, we will assume 10 Tesla as well. It will not go to anywhere. Principle conservation of energy. How many flux we have here? How many flux will go through here? So we know that this is a VGA because we took the VG, the magnetic flux density in the middle of the air gap. Then area is the area of the ST. If let's say we want to equate to find the WTB so that's why flux 1 equals to flux 2. It must be the same. So flux SP, this one must be equal to flux tooth body, whereby flux SP is a VG times AST. All the fluxes flowing through this area will equals to all the fluxes flowing through this area. Okay, so my V set times A tooth body. V set means we assume all the fluxes flow through here will achieve the saturation limit. This is what we want to design. We cannot simply put any value, or else it becomes under design or over design. We will assume all the fluxes flowing through this area will go through this area. Okay? So VG is already calculated. Okay. What about AST? AST is this length times LA. Okay. So this length, how to find this length? In order to find this length, we need to find the diary first. The parameter S equals to 2 pi R, which means the radius is RSI, right? Maybe I draw a little bit. the area, the radius is RSI. We want to find the parameter first. S equals to 2 pi RSI. And then how many slots we have? Because we have a lot of teeth, right? 1 teeth, 2 teeth, 3 teeth, 4 teeth, until 12 teeth. So only this, let's say only this length, we use all the parameter divided by 12 slots. This is the arc. That's why, so let's say this W, WST is equal to 2 pi RSI divided by number of slots, which is 12 lah. This is 12 lah. So this is a WST. Let's say this one is WST. This one is WST. So which means we times WST times LA. WST here times LA. And then we have a V saturation times ATB. ATB is WTB times LA. So WTB times LA. Something like this. So now we want to find the WST first. Because VG we already have it. WST is a 2 pi RSI divided by number of slots as according to here. And then we copy down LA equals to V set times WTB times LA. So from this given value, VG we already calculated. VG we already calculated from the here equation number 2, which is a 0.8296. So this one is a 0.8296. 2 pi is only calculated, number slot given, which is 12. RSI already given. How much? RSI is 27 nm. So 27 nm. Then LA is a 50 nm. V set is 1.6. V set is a 1.6 here. So 1.6. And then WTB is the thing that we want to find. LA is a 50. So we have this value. We have all this value. Only this one we don't have. Then we will calculate this value. Okay. So come back to here. Figure 1 shows the stator 2 dimension and it's a flux path per slot page. The magnetic flux from permanent magnet will cause an air gap. From permanent magnet will cause an air gap. Let's say this is permanent magnet will cause an air gap. Okay. From permanent magnet will cross the air gap and then go to the stator teeth. So therefore the total flux per stator tooth is this one given by here. So which is a BA and then G ST saturation tooth body. After that we use left hand side first. So left hand side is BG times AST. BG times 2 pi RSI over NS, which is this one. 2 pi RSI divided by number of slots. After that, what else? Then LA. So we calculated this value. Then assume the saturation level of the flux density in the stator ion and the rotor ion V set is not more than 1.6. Therefore, the right hand side, this one, is a flux stator pole equal to V set times ATB. ATB is a WTB times LA lah. Which means this one, WTB times LA. Okay? And then, so we calculate WTB. Then we found it's a 7.33. So class, remember, we will choose the nearest 0.5, which is more than that. So 7.33, we will choose 7.50. So this is the tooth body chosen. So calculate the thickness of the stator yoke. So figure 1 shows the total flux of stator pole passing through the tooth body. Usually it's split into two halves. Okay, for example like this. go in, then you split into two halves. Okay, and then one half enter the right hand side, another half go to the left hand side. For example, crossing the center yoke area ASY. So where it will cross? It will cross this area. Okay, so the ASY is actually WSY times LA. WSY is here times LA. Okay, and then let me finish this one first. Therefore, a coefficient of 0.5 of WTB is employed to avoid the magnetic saturation effect occurred at the stator yoke. So we will just use a 0.5 times WTB actually, because all the fluxes here, it will split by 2. So all the fluxes will give us WTB, and then half of the fluxes will flow through here. So we just use this area will be 0.5 times WTB Just a coefficient, and then additionally, two halves of the magnetic flux that passing through the stator yoke are highly influenced by number of slots of pole. Okay, these things is highly influenced of the number of slots per pole. So at the top we already calculate it. Then we just put the value here So WSY is varied for different PM machine with either a non-overlapping or overlapping winding configuration. Using 1 and 5. So this is number 5, right? Then using 1, where is it? What is this one? Okay. Then we can calculate the WSY. So the WSY calculate 12 slot divided by 10.5 are coefficient, 7.5 is from here. Then we'll have a 4.5. And then 4.5 chosen will be 4.5. Okay? So we'll rest for 10 minutes, maybe 5 minutes, then we'll come back to the graph again. Okay?